I won't ask you if the name Pavlov rings a bell. But when you think of Pavlov, what you'll probably think of is his explanation of Pavlovian conditioning. There have been a lot of others since then, but they're not well represented in the textbooks. What Peter's going to give us is an overview of alternate accounts of Pavlovian conditioning. Here.
As you can already tell in the Timberlake taxonomy, this is a relatively clean-shaven talk. And the font sizes are wrong in the back. Let me know, and I'll talk some more. So what I took as a task for this talk is to review how our ideas about association have changed. And the initial assignment was to do it just for the century. But I decided that I'd do it for a couple of millennia instead. And first I want to start by thanking a lot of people who contributed to some of the data and certainly talking about the ideas that I'm going to talk about today. So there's the list. And as we go along, I'll try to remember to specifically thank people. But to begin the talk, I want to go back 2 centuries and put up what our history of psychology textbooks tell us Aristotle said about association. I don't know if he really said this about association. At least what I read, it's a translation. It's reading someone else's lecture notes. That's like the election have to like mine. And it's hard to know whether the translation of the words really means what the history books tell us. But he might have said something like this, which is, and actually he was talking more about remembering and recall than he was talking about association. And so he's talking about what makes for a good recall cue. And he did say something like, well, when things appear contiguously, one thing is a good cue for another thing. And perhaps he meant that when it was near, it was both near in time and near in space. And when things were similar, they acted as a better recall cue, or association was formed better in our language. Another one that he mentioned was contrast. And what he had in mind there was, if I say up, what do you think? Right? Down. And somehow that connection is there, but we haven't studied that one very much. So, but yeah, that is okay. And then he may or may not have said, depending on which history book you read, that the frequency of contiguities was important in establishing associations. I think that it's more an inference from what he actually said than an actual statement. At one point he said something like, sometimes things are better retrieval cues even though they haven't appeared together frequently. And then so by inference maybe things that appear together frequently usually are good retrieval cues. But in looking at this list, it's actually kind of discouraging to think of all the new principles we've discovered in the last 2,000 years. And the progress that we've made, certainly we've done more recently a lot of studies about contiguity and a lot about frequency, not so much about contrast, and some on similarity in the formation of association, but again, not a great deal on it. And because this is the Society for the Quantitative Analysis of Behavior, what I want to do is skip 2,000 years and show you the first quantitative expression that I could find about how associations are formed. And what's kind of interesting, it was from Shukarev in 1907, and it's cited in an article by Gilkison, which was published in 1934. And it's actually the Gilkison article is a great article. I recommend it to everybody about a summary of quantitative models of learning. But so in 1907, at least then, someone gave a quantitative expression which has two underlying assumptions which have really stayed with us. And I would say they're the dominant assumptions of learning theory for this century, which are that learning is proportional to what's left to be learned, and also that the learning rate remains constant throughout learning. And a lot of the models, although they differ in some details, they have those as their underlying assumptions. And he just expressed it in terms of this differential equation. And he actually, his form of it was actually explicit in terms of it's what's left to be learned that's changing. And he did it in terms of time of practice, not in terms of number of trials, which is the way we do it now. But the basic idea was expressed here. And you'll see in a second some more familiar forms of it. What association theory in the century has done is focused on how the strength of a connection grows. And some of the models are expressed in terms of associations between stimuli, SS models, or between stimuli and responses. What's a functionally equivalent form is that learning is actually all or none in stimulus sampling theory, but what differs is the proportion of elements in a stimulus set which get conditioned on a given trial. And these assumptions are embodied in some models which probably a lot of you are familiar with. So Hole's model was in terms of SR connections, and he talked about habit strength growing in this way. And again, all of these embody the idea that what's learned is a constant proportion of what's left to be learned on every trial. And you can see as here, as the number of trials increases, this becomes small, and so habit strength approaches 100. It appeared in two other forms in the 1950s as stimulus sampling theory and as linear operator model, as expressed by Bush and Marsteller. And again, the underlying idea behind it is the same. And it's in all of these models, it's that what it's just on any given trial, on the first trial, there's on the first trial, there's so much to be learned, goes up a constant proportion, there's this much left to be learned in proportion to the next trial, and so on. And so what that gives rise to is, if you look at the associative strength, is the typical learning curve, the negatively accelerated learning curve. And so it does a good job of characterizing it that way. And then kind of the next thing that happened was there were some variants of it, which were that the learning didn't always start with the very first trial. There was a period of time that took place where nothing was happening, and then learning started, and then it pretty much followed this sort of a function, but this is more ogival in shape. And the problem for the models was that if you took the learning rates that you needed to fit the data once the negatively accelerated part of the curve was on, that you really couldn't say how long the previous baseline period was when it wasn't happening. And so that gave rise to things like two-phase models or two-state models, Markov models. And so it introduced another slight complexity to it. But still the basic underlying idea was once the learning started occurring, it was a result of contiguity, and each pairing contributed to the growth of associative value in this way. That is constant proportional. Now, what happened in the 1960s, I guess, was there began to be some empirical data that really put a strain on contiguity theories. And like Peter, I hate people who cover up their overhead. Except when I made the overhead, I didn't realize that I needed two of them. Okay, so here's the first one. And work on largely done by Bob Riscola in the mid-60s, looked at the effects of introducing unsignaled reinforces unsignaled unconditioned stimuli during the intertrial interval. And what it's a really good test of contiguity theory, because if you look at the two conditions here, the unconditioned stimuli are presented right after a cue, and nothing during the intertrial interval here. They're presented after the cue, but also during the intertrial interval. If all that was necessary for learning to occur was contiguity, those two conditions should be equivalent. And of course, you know that they're not. There's good excitatory conditioning in the top case, and there's very poor excitatory conditioning in the bottom case. So the way people approached it was to come up with ideas that to talk about the predictiveness of the cue, that in the top case the cue is predictive of the reinforcement, in the bottom case it's not so predictive. And to talk about it in terms of correlation, and to use correlation metrics to describe that relationship. And the assumption now that underlies that is that learning is no longer the result of just these discrete events, pairings of discrete events, but that things are accumulating over time. And it's usually expressed in terms of some sort of a contingency matrix, where there's a frequency with which the conditioned stimulus is, over time, accumulates with respect to the unconditioned stimulus in the presence of the conditioned stimulus. The conditioned stimulus occurs without the unconditioned stimulus. Maybe the unconditioned stimulus occurs without the CS, and the absence of both events. And those experiences are accumulated over large periods of time, and from that is extracted something that determines whether or not an excitatory response occurs. But it's very far from a contiguity view of it. And people looked at a couple of different kinds of metrics. They looked at delta P and phi, which are just given this way. Delta P is just the probability of the US given a CS minus the probability of the US in the absence of the CS. Phi coefficient is like a correlation coefficient. And delta P didn't work for a lot of situations. So, for example, if the probability of reinforcement in the presence of the cue is 0.4 and it's 0 in its absence, you get really good excitatory conditioning. But if the probability of reinforcement in the presence of the cue is 0.8, the probability of reinforcement in its absence is 0.4, same difference, you don't get such good excitatory conditioning. And so delta P wasn't when I worked with the phi coefficient, did a really pretty good job of summarizing a lot of the data. His were Scola's data, where he went through a pretty broad space of different probabilities in presence and absence of the cue, and here is just plotted as a function of the phi coefficient. So it looked pretty good for the correlation stuff, and pretty bad for contiguity for a while there. Except that there were a couple of other pieces of data that didn't fit quite so neatly. And they were on the slide that I should have made. The rest of this slide. And they were overshadowing blocking and relative validity experiments done in the late 60s and early 70s. And in those kinds of experiments that I've just illustrated here, if you have a QB and it's paired with an unconditioned stimulus, you get a nice big CR. All you have to do is make it part of a compound. And when you go ahead and do that, you test B, you get a little bit less of the CR. That's overshadowing. If you initially train A, so that it's a good conditioned stimulus, then compound it with B and continue to train it, do the same number of pairings as you did in any of these cases, you get a very, very diminished conditioned response. And so that certainly poses a problem for any kind of simple contiguity theory, right? Because in all cases, B has the same number of pairings, and it's a little bit of a problem for the contingency theories because you don't have anything happening in the absence of B, certainly in this case. So it's harder to explain in that way. And so it gave rise to a different type of theory. In fact, it was a type of theory which I am characterizing as the rescue effort. And Scholar and Wagner managed to salvage this idea that actually both ideas, that what learning is in these procedures is the result of just contiguous pairings, and that the amount that's learned is a constant proportion of what's left to be learned. And you can, the assumption that they made, which got them out of the hole, was just that the value of a compound is the sum of its elements. And that on any given learning trial, the increase in the value of a particular element depends on the learning rate times the discrepancy between what's left to be learned, the discrepancy between asymptote and the current value of the compound. And you can see how that gets you out of a lot of problems, because if you have a compound cube, if you have a single cube, then there's no interaction. But as soon as you have a compound cube, to the extent that, say, QX is learned about, it's going to diminish this discrepancy, and so you get overshadowed. If you do want to do blocking, you can see why that works in blocking, because if the value of A is high from an earlier phase of the experiment, then the discrepancy is small, and so you get less associated values in the second phase, to the new cube, the second phase of the experiment. In the case of contingency effects, the way that works is you have to think of when you're pairing a cube, the cube is also in a context. And so when you do something like a random control procedure, what you're doing is you're conditioning the context. Right? So its context is getting value, and that's one of the elements of the compound. So now when you do the pairings with the cube, there's less for that cube to get. And in fact, as what the model actually shows is, depending on the probability of reinforcement in the presence or the absence of the cube, you get things in this contiguity model coming out just fine. So, you get no associative value when the probabilities are equal. You get excitatory value when the probability of the CS, probability of the US in the presence of the CS is greater than in its absence, and you get inhibitory control when there's a higher probability of reinforcement in the absence of the unconditioned stimulus present. So far, contiguity theory is fine. But then another challenge to contiguity theory was mounted by people who got interested in time. And part of the underlying reason why this might be a problem is association theory is largely expressed in terms of point events that don't have any temporal duration and extent. And to the extent that that's important, then you have to somehow turn something with duration into a point event to make the contiguity theory work. I'll say that another way in a second, then you may understand it. Okay, but the things that were manipulated were things like the interstimulus interval, the time between the conditioned stimulus, the unconditioned stimulus, or sometimes called the trial duration, or what was varied at the time between the pairing episodes and the intertrial interval, or the time between reinforcers is sometimes called the cycle time. So that was the kind of manipulation that took place. And you can see that the sort of effect that's described is that in delay conditioning, when the unconditioned stimulus is very proximal to the conditioned stimulus, you get good conditioning. Introduce a little bit of gap, it gets worse. Introduce a bigger gap, it gets even worse. And so it's not inconsistent with an idea that some kind of contiguity is changing and the contiguity is getting worse. And the earliest ideas about what might be changing actually go back at least Pavlov. And the idea is that what's happening is that when a stimulus is presented, it creates some kind of a neural trace of that stimulus, sensory trace of the stimulus, and that over time, once the stimulus is taken away, over time that trace is getting weaker. But there still is a trace, and it's that trace which is contiguous with the unconditioned stimulus, which is responsible for the learning. And so if I turn a stimulus off, and as long as I have some trace that changes in an orderly way with time, there's going to be a unique stimulus, a trace stimulus, if you will, which can be associated with the unconditioned stimulus. But as probably a lot of you know from studying trace and things, not all traces are created equal. Let me just say one thing about time. Sorry, Russ didn't give his church didn't give his talk first. But one of the things that you want to make sure, if you're talking about how things change in time, and a temporal Q, is that Weber's law holds across a pretty broad range of times, and something like Weber's law. In other words, you want the discriminability of this trace up here and the discriminability of the trace down here to be proportional. That is the amount you have to change it to be proportional. And you can show that that works for some kinds of traces and not for others. John Stadden has made that point pretty recently. And it works very well for hyperbolas. So if you have hyperbolic decay functions, what you can do is you can show that Weber's law, the Weber fraction for time in a hyperbola is given by this expression. And this expression does depend on the time itself, so it changes with the time interval. But when t is very, very much bigger than b, as soon as t starts getting bigger than b in its generalized form, then this term drops to 0, and then the fraction for time only depends on the Weber fraction for the sensory system, or whatever the trace system is that's actually encoding the information. And I just show that here. You can see it actually graphically here, and it's just that in very, very short intervals, the Weber fraction comes down in a hyperbolic trace, but then it levels out and stays pretty constant across a broad range for particular parameters such as. But then an exponential decay, that's generally not the case. So you can have hyperbolic traces and still preserve Weber's law, which is what you want to do. So far, we can actually get the things we want out of a trace model and preserve the contiguity model, right? Except for one problem. And the one problem is that the strength of the association doesn't just depend on the temporal distance from the conditioned stimulus to the unconditioned stimulus. It also depends on the duration of the intertrial interval of the cycle time. So here I've illustrated a procedure where there's some distance from the conditioned stimulus to the unconditioned stimulus, right? Same distance from the conditioned stimulus to the unconditioned stimulus. In this case, you get very strong excitatory conditioning in this case. So it's not just the distance. That point was made in a much broader way across a broad range of stimuli by Gibbon and Balsam in this classic point of the data. Right. In which it's just showing acquisition speed in order shaping experiments as a function of the ratio of the duration of the cycle time between trials to the duration of the conditioned stimulus. In case anyone doesn't know order shaping, it's just you take a key light, you pair it with some grain, leave it on for a few seconds or longer, pair it with some grain, and after a few of those pairings, the bird runs over and pecks at the key light. So let's plot it with the acquisition speed. This is actually shown in another very nice way, that the effect of an interstimulus interval depends also on the trial interval in this plot where the data were replotted recently by Gallisto and Gibbon. And it just shows acquisition speed as a function of the interstimulus interval. And if you hold the intertrial interval constant, you get that nice delay function. So as the interstimulus interval gets longer, it takes longer to acquire the association. But if you change the intertrial interval proportionally, or the cycle time proportionally, then the acquisition speed remains constant. Right? So it depends on that relative time. And so what do you do when contiguity fails? You accumulate, right? That's the general strategy. And I'm going out of chronological order, but I will present it in this way, for the symmetry of the talk. And what recently Gallisto and Gibbon suggested is the basic one way to think about how these things are learned, is that both time and the number of events are accumulated over the course of experiences. And there's just the running register, how much time do you spend in the conditioned stimulus, how much time do you spend in the intertrial interval, when do you get reinforcements, and the animals make estimates of the rate of reinforcement in the presence of the CS, and an estimate of the rate of reinforcement in the background. And because the rate of reinforcement in the CS is the sum of the rate of reinforcement during the Q plus in the background. Whenever that exceeds by some threshold beta the rate in the background, that's when you see responding. And you can see, this gives you that kind of relative time effect very easily, because if you just multiply the rate of reinforcement in the Q by some constants and this rate of reinforcement in the absence Q by some constant, then everything increases proportionally, the ratio remains unchanged, and so you get that relative time effect. But, so this is an accumulator model of those effects, but if you allow me to distort history for a moment, contiguity is in trouble, and we need someone to say this. So, whoops, more Q. I'll get there in a second. Here we go. Here. All right. So Gibbon and Balsam are about to say the contiguity before it needed second. And the assumption in that version of how associations form was pretty interesting. It preserved the idea that what was underlying the learning was a pairing, the contiguity of the conditioned stimulus and non-conditioned stimulus. And it also preserved the idea that it was a proportion of what's left to learn. This was learned on every trial. But the way it introduced the time was to say that the asymptote of conditioning was inversely related to the durations of the cues. And so that when, as the animal experienced repeated reinforcers, what happened was there was an expectancy that was formed in the presence of the cue, which was like the average, it was just the duration of the cue divided by the arousal or the overall expectancy. And also at the same time, the animal formed the background expectancy, which was the expectancy divided by the cycle time, the time between the reinforcers. And over trials, what happened was just a basic linear operator model that here is just illustrated how it would grow over trials. So initially in these experiments, you teach the bird to eat from the feeder, so there's conditioning in the context. And that happens pretty rapidly, and so the expectancy in the context goes up pretty close to asymptote. Then you introduce pairings, and what happens is that the expectancy in the trial starts to grow, and it goes up. And then when the comparison of the ratio comparison of those two values, right, just the expectancy in the trial to the expectancy in the background, and that just reduces to the C over T ratio, and that's greater than a threshold. And so this model predicts that the acquisition speed should be a function of that ratio of cycle to trial time. And is it, do we know yet, is it a function of the ratio of cycle to trial time? Oh, yeah, it is. Yeah, right. It still is. Okay. All right. Now, think about what underlies even that notion. What underlies that notion is that somehow times between events are learned very rapidly. I mean, this is really saying, for that to affect asymptote, that somehow the time between events is already appreciated before acquisition is occurring. And so what we'd like to do is know when does this time start to be appreciated in the development of these associations. And I'm going to have to go a lot faster than I've been going. Yeah, okay. All right, so we look, there's been some examples that indicate that, in fact, time may very well be an inherent part of what's learned right from the very start. I'll just give you a couple of examples. There's an experiment by Fanslow and Stowe where they put a rat in a box, some rats in a box. 3 minutes later, they give them one shot. They bring them back and put them in the box, and they look at and this is the percentage of subjects squeezing. So with a single experience, right, that there's a temporal gradient around the time of shock from that single experience. With Mike Drew and Kai Kuvalon and Jeff Bitterman, we did some conditioning in goldfish. Here's a picture of acquisition of activity conditioning. In this experiment, when the light comes on, 5 seconds later, there's a shock. And then we look at the On some trials, we then leave the light on for 45 seconds. And we look at the temporal gradient of activity during the light. See what happens. And here's the first 5 sessions, and the next 5 sessions, and the next 5 sessions, and then the last 5 sessions. And what it looked like was that right from the beginning, there was some kind of temporal control, and the peaks marched up, but that's a pretty big block. So we also looked in the first 5 sessions, and we actually modeled it in terms of a version of scalar expectancy theory. And what's important for the discussion today is when you look at where the peak times are, where the middle times are in those distributions, even in the first 5 sessions, even from session 1 through session 5, there's no significant change in those peak times. Now, it is the case they're more and more likely to respond, but when they respond at about the same time. There's a really neat experiment that Tatsuya Oyama just told me about, which he's doing in Mike Mock's lab, where it's eye blink conditioning. And what he does is he conditions the animal with a short interstimulus interval, and he stops conditioning before they show an conditioned eye blink. Then he trains them with a longer interstimulus interval until they start blinking. And he looks at the form of the response, and sure enough, there's a peak, there's a blink at that earlier time. So it looks like, even before we see anything like acquisition, that those temporal relationships are in some way appreciated. And now, I want to say, I think it's going to be the major challenge to contiguity theory in the next century. And it's based on the idea that, I guess we said a long time ago, regular properties of display are perceived as patterns, which are superordinate to their elementary constituents. So that when I show you this, you learn about that pattern. And you learn that there are squares, and you learn that there are circles, rectangles, and circles. You learn about the spacing of those things. And in fact, you learn about the relative spacing of those things. And that what I now want to argue is that we do the same things with events which are presented in time. And I guess I want to argue a little further that what it is that we extract from those kinds of experiences, like these kinds of experiences with things in space, is something which is analogous to a map. And I don't exactly know what I mean by that, but whatever the superordinate stimulus is that is controlling our behavior with respect to that display, I want to argue that a very similar thing happens when things are presented in time. And I'll do it. Okay, so here's the claim. You experience things over time in a conditioning procedure like this. And that what's learned is the pattern. And not only do you just learn like a general qualitative pattern, but the pattern has metric properties, and you learn about the specific durations of time. And that's part of what we mean by learning the pattern. And that it's like a map, and the map has Euclidean metric properties. Okay, first, spatially. Suppose let's be Bill Timberlake, we go foraging in the field, and we find red berries in certain places in the field. It doesn't take you, if I ask you where are you going to go look for red berries, it doesn't take you very long. Right? You're going to go into this field, you're going to look at the right side of the group of the rectangles. And that's a pretty easy pattern to detect. On the other hand, if you were confronted with a field that looked like this, you would not extract that pattern very readily from this kind of a spatial display. Okay? Now, in the temporal domain, I'm sure most of you have realized by now, this is exactly the difference between a positive contingency and a random control. Is that in temporal domain, there is a good temporal relationship between the Q's and the uppercase, and a not very clear pattern of occurrences in the lowercase. And of course, as you know, in the upper case, you get good conditioning. In the bottom case, you don't. Okay, here's another example. Yeah, I know, I did that. Yeah. I'm moving ahead. Yeah. Here's the unreliable cue again. Now, look what happens to the perception of pattern when I add an additional cue for all of the ones that were not previously, if you will, signals. Right? Is when I add that additional cue, it's much easier to pick out this relationship. So now if you went out into the field and I said, where are you going to look for the red berries with respect to the blue rectangles, you would be able to do it pretty readily. Whereas if this had been this had been the experience, I'd say, where are you going to look for red berries? You'd say, I don't know, around somewhere. So in the temporal domain, that's a different sort of an experiment. What that experiment is the random control. Right? That's the unreliable cue. And then what you do is you add an additional signal over the intertrial reinforcers. So those are signaled intertrial reinforcers. And we know in that domain that surely this doesn't generate very good conditioning. Now how about when you cover the reinforcers, does it generate good conditioning? Well, Durlak, a number of people have done experiments like that. Durlak did one of the early ones, and here's responding to the target cue. When the intertrial reinforcers are unsignaled, you get very little responding. When the intertrial reinforcers are signaled by a different cue, you get very good responding. So the pattern emerges again once we have the additional cue. It was Cooper, Aronson, Balsam, and Gibbon actually showed that the temporal domain, once you add that added cue, it's as though the pattern is extracted from only all the remaining time. That it works kind of in that direction. Another thing that's true of spatial maps is that they survive transformations of scale. So you can learn this map and you won't have any trouble finding the locations on this map, or learn this map, you won't have any trouble going that way. There's an equivalence over transformations of scale. Now how about in the temporal domain? If you just do scale transformations of the durations, are those things in fact equivalent? And let's see if that's true. Oh, yeah, it's still true. In the temporal domain. Okay, another example is, or another way of saying that things that are relatively spaced go, what happens when you relatively space them. Here are things which are tightly spaced in the spatial domain. Here are things which are more widely spaced. Right? And it's you just look at it, and it's much easier to extract the pattern out of this than it is to extract the pattern out of that. So that's like our trial spacing effect. Okay. Then another interesting thing about the trial spacing effect, I can illustrate with this idea, which is that if you live in London, the distance between London and Paris is psychologically quite large. If you live in New York, the distance between London and Paris is much smaller in terms of how that's represented. Now, what happens if you're a New Yorker who goes to London? How far away is Paris? Well, the answer turns out to be it's somewhere in between. That it's not as close as you thought it was when you were in New York, but it's not also as far away as a person in London. And so the distances are weighted, right? Or the psychological assessment of those distances is weighted by both the relative, it's really weighted by the relative duration. So how far away you are from this representation and how far away you are once you're here. And both of those things contribute to it. So I once fooled around with an expectancy metric that kind of captured that idea for Pavlovian conditional. And in that, so here's the relative proximity effect. Is this the same slide you saw before? This is good excitatory conditioning. This is bad excitatory conditioning. But how excitatory this is depends on its relative time here, but it also depends on how relatively far you are here from here. And so it's also the relative time within this interstimulus interval that has an influence on the overall excitatory strength. And just without exactly going into what the metric is, here's just some trace conditioning studies that are plotted as a function of this expectancy, weighted expectancy ratio. And it's a pretty good fit. It's in the right direction. And you get some even more interesting data. And they were collected by Peter Kaplan a while ago on approach and withdrawal. And what he did was he varied where in an interstimulus interval the conditioned stimulus was. And he just moved it around throughout the interstimulus interval. And what he got was when that cue was relatively proximal to the reward, you got approach, a strong approach. But when that cue got more and more remote, he got less and less approach, but then he got withdrawal. So when that cue was kind of in the middle of that interstimulus interval, that animal knew about that cue just fine. It knew a lot about it. It learned a lot about it. And it learned a lot about the temporal relationship. It's just the behavior that was evoked was quite different. It wasn't the terminal excitatory behavior of approach pecking at it. It was, in fact, withdrawal from that cue. And so, okay, then I know, let me just say one thing, okay? And these maps, right, are concatenated and integrated. You can integrate maps. And they're integrated over time as they're built up. So in an experience of events over time, a map starts to be created and another experience happens and it's added to it. But you can also integrate independent maps. So you learn this problem, right, and you learn to where to look for the red arrows. And then what I do is I show you here. Okay, now I show you this. Okay? And you learn the relation, and now you learn the map of the triangles to the rectangle. And then my next step is, as you probably have already guessed, is where do you look for the red berries with respect to triangles? And most of you will look over here, right? And so what you've done is you've taken the information from the first map, integrated it with the second map, and so you get that, if you will, what we usually call inference from that. Does it work in the temporal domain? Sure it does. There's an experiment by Cole, Barnard, and Miller in which the two conditions. First, this is first order conditioning. So a cue is delayed conditioning, and the unconditioned stimulus is presented right after the cue. It's a 5-second cue. In trace conditioning, there's a 5-second gap from the end of the unconditioned stimulus until when the unconditioned stimulus is presented, and you get the usual effect. Trace conditioning is worse than delayed conditioning. So you get the usual stuff. Okay, now what they do is second order backward conditioning. What they do is they present a new cue after the first order conditioned stimulus. Right? So they're going to present this new cue right after the conditioned stimulus here and right after the conditioned stimulus here. Now, to the extent that the strength of association depends on the strength of the thing that it's paired with, right? You expect good conditioning first order cue, you should get good conditioning here and worse conditioning here. But if what they've done is created a temporal map of those two things, then what's going to happen is the second cue occurs at the same time as the reward here. Here it occurs just before the reward was expected to occur. And so if those two maps are actually integrated with each other, we might expect strong anticipatory responding here as opposed to there. And sure enough, that's what you get. That the second, if you will, the response to that cue is stronger in the case where it filled the gap. So, all right, so in conclusion, I think the big challenge for contiguity and for frequency is lost. The next one here. Okay, here it is. So here's the strong claim. Events are represented in a temporal map that the metric properties and they have the metric properties of Euclidean space. So they survive transformations of scale like the similarity relation Euclidean space, and maybe they survive all the other Euclidean transformations as well. They're integrated over successive experience. It's probably that things have common elements, which allows the integration of the maps. That separate maps, in fact, can be integrated, and that gives rise to what we often refer to as inference. And as a final point, well, how does that then get translated back into behavior? Is that I think one of the strong determinants is that it's the relative temporal relationships which determine actually which response is evoked by that cue. Thank you.
I've already heard from you, Gene. Is there another question? Yes.
Is it possible that contiguity theory in all its parts is simply a fallback or default condition for learning?
Try that again. What do you mean fallback?
If everything else fails, try contiguity.
Okay.
It reminds me of something Neil Miller once said. The Pavlovian condition is a good way if you have a very dumb subject. The cat seems to get the idea.
Contiguity theory has been really robust. And I think it boils down to whether you can construct higher order relationships between things from more elemental kinds of things. And in general, you can figure out ways to do that. Right? And so I'm open to it going either way. I mean, at the moment, I see this kind of pattern learning thing as a pretty good challenge to what our current understandings of how contiguity works. And whether or not we'll come up with a contiguity theory that actually can be built up into these other things is certainly a possibility. So that's sort of one level of answering it. The other level that you might invent it is other multiple learning mechanisms. And I think probably yes.
Okay, I'm going to take one more question because we have 55 seconds. I'm going to give mine to Billy, but I'm going to make a few announcements after that. So hang tight after me once again. We'll be thanking Peter. Bill?
I'm actually a little surprised that you're using the word contiguity in talking about what appear to be extended patterns in time, where I guess you and I have different histories with respect to that word. I always think of contiguity as referring to moments in time and pairings in time. Now it struck me you moved far away from that. You're talking about these.
I guess I haven't communicated well. I completely agree with you. The sense in which I've been using contiguity is between things that are close together, point events that are close together. And so I've been seeing this pattern learning as a challenge to that theory.
Yeah, okay.
Right.
Then talking about how contiguity has been a robust idea and saving contiguity and so on seems to be contradictory, actually.
Well, I think the history of thought about this for a while has been in terms of contiguity. And the dominant explanation for the effects of these procedures has been in terms of contiguities. So it's in that historical context.